Okay, welcome back to our second video on electric fields. We said that we were going to leave off with this example. What this example is showing is a contraption called a system of parallel plates. Parallel plates are exactly what they sound like. Two rectangular plates, usually metal, so that they can store charge, and they're parallel to one another. Now, usually they're very, very close together. You can just imagine this is very zoomed in. And we're imagining that these are actually really big. They're taking up a lot of space. We want to know what the electric field is inside the set of parallel plates. We don't care about outside, we care about inside. So let's imagine putting a test charge here. It's a test charge, a little positive charge, is really close to these positives, so it's going to get repelled very strongly. It's going to get attracted to these negatives. So you might think, oh, well, then the electric field would point down. The only question is about the size, how strong the electric field is. Think about it. As it moves away from the positive charges and the repulsion from the positive charges gets weaker, it's getting closer to these negative charges and the attraction would get stronger. It turns out that this is exactly balanced out. So it turns out that the electric field inside a set of parallel plates is uniform. This has a lot of interesting applications. And it always points towards the negative plate. Since the negative plate is down here this time, the electric field is going to point down. And since it's uniform, the way I need to draw this is I need to space the plates, space the lines out evenly. Because remember, the spacing of the lines tells us the strength of the field. So I'm going to do this. I'm only going to draw 5 lines this time. But they would look like this. Okay, there's the electric field for a set of parallel plates. Now, some applications for parallel plates. This calculator actually works because of the electric field between parallel plates. Under each of these buttons is a set of parallel plates with an electric field between them. There's a computer in here that can sense changes to the size of the electric field. When I push down on this particular button, I'm compressing these two parallel plates under the 8 together. That's actually going to increase the electric field inside the plates, and the computer senses that, and it reads that the electric field under this button has gone up, so it enters an 8 on the screen. Parallel plates are in calculators, they're in basically all different types of buttons that you can have. Another application that we found for parallel plates is that we can send charged particles through them and redirect them however we want. Imagine I have a little electron here, and I'm about to shoot the electron in to the parallel plates at a very high speed. Electron, so I'm going to put a little negative there. What's going to happen to the electron as it goes in? Well, it's going to get repelled from the negative, because remember, negatives repel other negatives. It's going to get attracted to the positive plate. Now, you might think it's just going to go and end up getting stuck on the plate, but we're shooting this electron in very, very fast. So I'm saying, like, the electron's really going to be zipping here. It's going to start to move towards the positive plate. It's going to exit the plates. And look, the direction the electron went in was basically parallel to the plates. By the time it gets over here, its velocity vector has changed. Now it's moving in this direction. So parallel plates can also be used to shoot charged particles in different directions. Matter of fact, this is how the first TVs and like computer screens, or maybe not even computer screens, but like electronic screens were done. It was a set of parallel plates shooting charged particles at a screen, and then they would hit the screen, and I think there was some sort of chemical reaction which would release some light, and that's how you lit up a TV screen, or not just any type of screen in the early days. So which way would an electron zipping through the plates move after it has left them behind? It ends up moving toward the positive plate away from the negative plate. Okay, so we're going to have that electron, its direction of its velocity is going to be altered because of moving through parallel plates. Okay, so again, 6 basic pictures that you need to know. You need to know and be able to pick out what the electric field will look like for these different distributions of charge. For the single positive and the single negative that are on the front, 2 positive charges, 2 negative charges, 1 of each, and a set of parallel plates. You need to be able to draw those electric fields if asked, or pick them out from a lineup, like if it was a multiple choice question. You need to be able to do that. Now, what I'd like to start talking about is not necessarily we've got the shapes down, but now we need to start talking about how to calculate an electric field. And what I want you to notice here is that we drew all of these using this idea of a test charge, like a little tiny positive charge that we put in here, and we imagine what direction the force on it would be. Putting the little positive charge in here, because it's so small, does not affect the electric field of the charges that are creating it. These charges create this field whether the test charge is there or not. Having the electron in between these parallel plates doesn't affect the electric field that the parallel plates have created. So one of the things that we have to remember is this. The magnitude of an electric field is based on the size of the charge creating the field, not on the test charge. The test charge is imaginary. It doesn't have to exist. Okay? It's the charges that were there to begin with. The one big positive charge, the one big negative charge, the two positive charges, the two negative charges, the positive and negative, and or the parallel plates. That is what creates the field. Okay? You can have a field created by just one charge. You don't need two charges. Once a test charge is placed in the electric field, okay, the electric field gets created by those initial charges, then you bring a test charge in. What happens is it is subject to an electrostatic force. That's what we've been measuring. That's Fe. The electrostatic force, if you remember, the equation for it in the simplest form is K Q1 Q2 over R squared. So since there's Q1 and Q2, the electrostatic force is based on both the size of the test charge and the charge creating the field. So we have a difference here. The force depends on the magnitude, the size of the two charges as they interact. However, the electric field only depends on one charge, or one type of charge, I should say. The electric field depends on the magnitude of the charge distribution that creates the field, not on the charge experiencing the field. To go back to our first example, or our examples, these charges, here, here, here and here, here and here, the two parallel plates, those are creating the field. Those are charges that are creating the electric field. That's why we drew the lines. The test charge that we were to bring in as we investigate these shapes does not matter. That doesn't alter the field. Okay? The test charge is just experiencing this field. It's experiencing these forces. Okay? These forces are acting on it. And the forces act because now we have two different sets. We have some charges creating the field and a charge experiencing it. There's a force exerted there. But without that test charge coming in, then there is no force. Okay? Without that test charge coming in, there is no force. Once we put the test charge in the field, it experiences that force, and that helps us to draw in the field lines. But the field exists whether the test charge is in there or not. Okay? That'll get a little bit easier as we do more repetitions with this. But the electric field can be created by just one charge, or a charge distribution, some setup of multiple charges. An electrostatic force can only exist if there are two charges there. There's an equation for the magnitude of an electric field, and it is in your reference tables. It is the second equation down on the electricity section. It is this. E, oh, that is really out of focus. E equals Fe over Q. Okay, the electrostatic force is Fe, or excuse me, the electrostatic force is Fe. Q is just a charge, and E is the electric field. E equals Fe over Q. We could rearrange this, and sometimes we do, into this format. The electrostatic force is equal to the electric field times Q. The units of electric field are newtons per coulomb, as you can see right here, newtons over coulombs. And as we've been drawing pictures with arrows on them, this is a vector quantity. Now, before we get to the examples, I do have one last point to make involving this Q. In this equation, that is on the reference tables, Q, is the test charge. The charge that experiences the field. Okay, so I just got done saying that the electric field doesn't depend on the size of the test charge, so why is it in here? I want you to think of it this way. If you have a test charge in an electric field, it's going to experience a force. Now that force is dependent on the size of the test charge and the size of the charge distribution. So Fe depends on the size of the test charge. But then Q down here is also the test charge, the charge that's experiencing the field, the charge that's getting a force put on it. So if we're accounting for it here and we're accounting for it here, it's kind of like those two cancel out a little bit. I'm not saying that this literally crosses off here, but dividing by Q, it looks like it's going to not make sense based on what I just said, but trust me, it does. Q is accounted for in here and in here. So therefore, we need to make sure that this is the test charge. This is the charge that's actually getting a force put on it. It's the charge that is experiencing the field. Now, as far as the units go, newtons per coulomb, that's a little confusing. It's, a newton, and we know is a unit of force. A coulomb is an amount of charge. The way I want you to think of this, N over C, or N per C, think of it, it is the ratio of size of Fe to the magnitude of the test charge. In other words, it's the amount of force per charge. If there is more charge, then a bigger force will get put on that charge in a certain electric field. Think of it kind of like a unit price. Like if you go to Walmart or BJ's or Sam's Club or wherever, and you're buying something in bulk. Like let's say you can buy like a 4-pack of something for $12. Okay, that means you're getting each item for really $3, but since there's 4 of them, you get it for 12. Okay, that's sort of what an electric field tells us. It's telling us like the unit price of the force based on how big the charge is. Okay, the newtons is kind of like the dollar amount, the charge, the coulombs, that's kind of like how much you're getting. It's how much force you're getting per unit of charge. Since we know the equation for the electrostatic force between 2 point charges, we can also write the equation for electric field created by a point charge like this. This does not come up that often, but I do just want to show it to you anyways. Fe over Q. We know the equation for Fe is K Q1 Q2 over R squared divided by the Q for the test charge. Well, that Q for the test charge is either Q1 or Q2. It doesn't matter which. So one of these sets of Q's are going to cancel out. Another way to calculate the electric field for something is like this. K Q over R squared. And in this equation, Q is the charge creating the field. Again, this doesn't come up too often. It comes up more if you take like a college level class. They use that equation a little bit more, but I just wanted to show it to you now. So I know we've got a whole lot of stuff going on here with Q, and is it a test charge? Is it the charge creating the field? Trust me, it's going to get simpler once you start getting into this. Okay? And ultimately, again, what we're focusing on, the reason we talk about electric fields is sometimes it's hard to find the electrostatic force using this equation. Sometimes this equation doesn't really apply. However, if we know the electric field strength, then we simply multiply the electric field strength by the charge that is in the field, that's experiencing the field, and we can figure out how big of a force is put on it. And from that, we can figure out the rate at which it accelerates. And from the acceleration, we can figure out where it goes, how fast it moves, how much time it takes, and stuff like that. Okay? So essentially, we use the concept of the electric field to calculate the electrostatic force in situations where using this, kq1, q2 over r squared, isn't feasible or isn't the right thing to do. Okay, finally, let's get to some examples. Number 1, the Van de Graaff generator can collect up to 8 times 10 to the negative 6 coulombs of charge on its outer shell. I promise in class, if we haven't yet, we will get this out and play with it. It's very interesting. It's kind of fun to play with. So, the generator can collect up to 8 times 10 to the negative 6 coulombs of charge on its outer shell. What would the magnitude of the electrostatic force, that's Fe, between the generator and a proton, that's going to be one of our charges, 0.3 meters away, that's the distance, be? Well, the Van de Graaff generator, once you see it, it's a spherical shell. So, since it's a spherical shell and we have a proton, which is a point charge, we can use the Fe equation. Fe equals k q1 q2 over r squared. K, from the reference tables, you'll remember, it's right on the front, is 8.99 times 10 to the 9th newtons times meters squared over coulomb squared. Q1, let's make that the charge on the generator. That's 8 times 10 to the negative 6th coulombs. And the charge of a proton, remember, is the same as the charge of an elementary charge. Protons have an elementary charge of plus 1e, and one elementary charge is equal to this many coulombs, 1.6 times 10 to the negative 19th. We need to make sure that this is in coulombs to use this equation. So 1.6 times 10 to the negative 19th divided by r squared. The distance between the two, 0.3 meters squared, Fe. Now we just got to type it into the calculator. 8.99 times 10 to the 9th times 8e to the negative 6th times 1.6 e to the negative 19th divided by 0.3 divided by 0.3. We end up with an electrostatic force of 1.28 times 10 to the negative 13th newtons. And again, remember, that seems really small, but in part C, we're going to see how big of an effect that actually has. B, what is the magnitude of the electric field created by the charge on the generator? We're solving for E this time. We know the equation for E is Fe over Q. We just solved for the electrostatic force between the proton and the generator. But the question is, what do we put in for Q? There's two different charges here. There's a charge on the generator. There's a charge of the proton. Here's how I want you to think about this. Just based on the kind of setup of the problem, you could probably guess that the generator charge is the one that's creating the field that the proton is interacting with. That's not the charge that goes here. The proton is the charge that experiences the field created by the generator. Oh, it doesn't create charge. I should say it creates the field. Excuse me. Since it's the thing that experiences the field, that gets a force put on it, that is the test charge. And I should clarify that the force is between both of these. The generator experiences this force, but so does the proton. But we're focused on the proton. We want to know the electric field where the proton is. We want to know what electric field it's experiencing so we can figure out how big or how, well, we want to know getting tongue-tied. We want to know the electric field at the location of the proton. So we take the electrostatic force that acts on the proton and divide by the proton's charge. That's what's going to go in for this Q. So 1.28 times 10 to the negative 13th newtons divided by the charge of the proton, because that's the test charge. That's what's experiencing the field. Okay? The generator creates the field. The proton experiences it. That's why the proton charge goes in here. 10 to the negative 19th coulombs. And we get, with some rounding, oh, let me do that. Make it a little better. 1.28 times 10 to the negative 13th divided by 1.6 times 10 to the negative 19th. We get an electric field of 800,000 newtons per coulomb. Now, what does that mean? That means that if you were to bring 1 coulomb of charge to the location of the proton, it would experience a force of 800,000 newtons. If you were to bring 2 coulombs of charge in there, it would experience a force of twice this, okay? So remember, the electric field kind of tells you like the unit price, the charge per, or the force per charge. Since we only brought a little bit of charge to where the proton is, it experiences a fairly small force, okay? But the key thing is understanding that this is why the proton is the test charge. It experiences the field. That's why we use the proton's charge down here. Now, let's link this back to forces and kinematics. If this electrostatic force is the only force acting on the proton, if it's the only force, that implies it's the net force. At what rate will the proton accelerate? What's the acceleration? Well, if F net is equal to the electrostatic force, I know that F net is also equal to ma. The electrostatic force is 1.28 times 10 to the negative 13th newtons. The mass of a proton is on the reference tables. 9.11 times 10 to the negative 31st kilograms. Times A. And we find that the acceleration of the proton is huge. Oh, it's a proton. Oh no, I used the electron. I'm sorry. Oh, I'm so wrong there. Okay, the rest mass of the proton is 1.67 times 10 to the negative 27th kilograms. Oh, I apologize. That was so silly. That's all right. Okay. 1.28 e negative 13 divided by 1.67 e negative 27. We get an acceleration of, still really huge, 7.66 times 10 to the positive 13th meters per second squared. That's a huge acceleration, okay? That's absolutely enormous. The reason it's so big is because even though the force is small, look how big that mass is. It's tiny. Last question, or last example for this set of notes. An electron is subjected to an electrostatic force of 5 times 10 to the negative 15th newtons. What is the magnitude of the electric field causing the force on this electron? We're looking for the electric field again. We're told the electrostatic force. We need Q. We know that this is going to be E equals Fe over Q. We got to think Q is the charge experiencing the field. It's the charge experiencing the force. It's the test charge, and it tells us that that is an electron. Okay? So what I'm going to do is I'm going to plug in Fe as the force that they told me. 5 times 10 to the negative 15th newtons. And I'm going to divide by the test charge, the size of the test charge, which is the electron, and that is 1.6 times 10 to the negative 19th C. And just like with the electrostatic force equation, you are not going to make this negative. Okay, there's no such thing as a negative electric field. You're going to plug this in as a positive, and then you're just going to think to yourself, okay, remember, this electric field points away from the positive charges towards the negative charges. All right, 5 times 10 to the negative 15th divided by 1.6 times 10 to the negative 19th. We get 31,250 newtons per coulomb is the electric field. Again, that's the ratio of how much force gets put on the charge, the test charge, to how much charge the test charge actually has. There's one more video where we'll do some more examples on electric field. We'll do that in just a second. I know this is a somewhat tricky topic, but stay with it. You're doing pretty good with it.